The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
We are exciting a band that, so you're exciting from low vibrational levels to a relatively high vibrational level, and this then fluoresces very far to the red. There'll also be some blue fluorescence from the two turning points. And so going from one vibrational level to another, the ratio of intensity in the blue and the red can change. And so usually these effects of the sensitivity range of the photomultiplier are qualitative, I mean quantitative. They don't make a line disappear, but they make the intensities of transitions that occur in the same region of the spectrum be different from what you expect.
Can you ever use that to your advantage?
Yes.
By having two photomultipliers and...
Yes. One often uses two photomultipliers and usually use some kind of filter, which will sort of divide the spectrum into two channels, and the two channels, the relationship between the two channels provide you with information, a way of sorting. You can also have a local perturbation where, so here's a term value curve, and here's another term value curve. This is energy versus JJ plus 1. And suppose this state is bright, it has a short lifetime, it's the state that you're exciting to. This is dark, you can't excite, you can't have an allowed transition from the initial state into this. It has a long lifetime. And near where these levels cross, you get an avoided crossing like this. Whoops. And the states are schizophrenic. The levels have intermediate radiative properties, and so you will end up seeing lines with anomalous intensity, with anomalous frequencies, and maybe more lines than you expect. So perturbations can also affect the signal. So there are many effects that corrupt the relative intensities. And you could also be doing an experiment like resonance-enhanced multiphoton ionization. So instead of looking at fluorescence, one could be exciting to this some intermediate state, and then with a second laser ionize. And that's also not indiscriminate. So now instead of looking at a photon, so you excite here, and there's a laser always present that causes that state to ionize. And so if this state does something, goes away by fluorescence or predissociation, you can still have intensity anomalies due to quantum yield being other than 100%. So there's lots of ways in which the intensity in a laser-induced fluorescence or a REMP spectrum where you're scanning the frequency of the laser is different from just the absorption coefficient. Okay. So when you do a spectrum like an LIF or a REMP spectrum, you have the same problem you did with the classical spectrum. You get the whole spectrum. And there isn't any sorting, so that you don't really know how to assign it. It's just as hard. In fact, it's harder because instead of having the whole spectrum all at once, you have to slowly scan your laser and you record the spectrum. And you're wasting a lot of time, because instead of getting 100,000 resolution elements in one shot, you're getting a resolution element every second or so. And, but you still haven't done any sorting. So there's a very simple idea. And that's dispersed fluorescence. So you have your laser populating some upper state, and you're not tuning the laser anymore. You've tuned it to a fluorescence line, and you stop. And now you look at the fluorescence from this upper level. And so this is a level which you would like to know its quantum numbers. And all you know when you start is that you've excited it. There's some fluorescence from a level. And you might even have, as you scanned at your LAF spectrum, you said, oh, this looks like a nice, sharp, single line. I'd like to know who it is. And so you stop and you say, okay, now I'm going to do a new experiment. I'm going to take the fluorescence and put it into a monochrometer or a spectrometer and measure the spectrum of the fluorescence. And so what you see is a series of pairs of lines. And what you see in the spectrum is nothing but combination differences. So the thing that you had to work on in the classical spectrum is given to you on a silver platter. That the spectrum, the dispersed fluorescence spectrum, contains nothing but what you wanted to know. So it's a fantastic simplification. And so you see a spectrum that normally looks like a progression of pairs of lines. And so these are P and R lines that come from a common J, and from the spacing of them, one knows something. You know that, so this is the P, let's call this J. This is the PJ plus 1 line, and this is the RJ minus 1. Yes?
So technically you still have to scan your monochrometer in order to get that.
Yes.
Same as scanning laser.
Well, it's even, first you scan your laser to a line, and then you stop.
Right.
And you scan the monochrometer, unless you have a detector, which is a two-dimensional detector.
Okay.
And that's wonderful, because now what you're doing is you're actually measuring the total intensity in each of the lines, and the intensities are meaningful because it doesn't depend on what the laser was doing as you were scanning the monochrometer. So, and most experiments, dispersed fluorescence experiments these days, are not done by scanning the monochrometer. They are done with a CCD detector. And it's just a television camera, and it says, oh, I see 2 lines. And so...
Did people ever do dispersed fluorescence spectra with lasers and photographic plates?
Yes, I did that. That's really stupid. But it wasn't photographic plates. You remember the Polaroid camera? Maybe that's what we used. So, you waited a few seconds, and you developed this thing, and you measure with a ruler on this still wet piece of film, that film paper. But it's much easier to, we also use chart recorders. You don't even know what a chart recorder is, do you? And in fact, one of the first things I bought at MIT was a 2-pen chart recorder, because I wanted to record the spectrum and the standard lines on the same thing, because no computer. And in fact, I think I had a 4-pen chart recorder at one point. Now, chart recorders are notorious because they're pens clog. If you've got 4 of them, you're basically never taking data, and it's because the stupid detector isn't working, not because anything complicated like a laser or the molecular source. And so this is where my conservatism about loading up an experiment with peripheral junk that might not work, the hard thing should be the laser and the source of molecules. And everything else should be 100% reliable. Chart recorders maybe it ruined my perspective. Anyway, so you get this progression of pairs of lines. And so you can calculate from the rotational energy level formula that the spacing between lines is going to be B double prime, the rotational constant of the lower state, times 4 J prime plus 2, the quantum number of the upper state. And so if you know B double prime, then you know J. If you know J, you know B double prime. You don't know either when you start. And so you do this, you tune the laser to a line, and then you tune the laser to the next line that looks like it belongs to the same pattern. So you want to look at 2 consecutive lines of a branch. Your eye tells you, yeah, that looks like a pattern. I believe it's a pattern. I look at 2 consecutive lines, and if the PR separations change by an amount reasonable for a change of 4B, then you say they were the same 2 lines, and you know 4B, and you know J. So 2 measurements. You look at the dispersed fluorescence from one line, and then what you think is the next line. And if you're not unlucky, then you have a complete rotational assignment of the spectrum. So these are give you the rotational constant of some vibrational state. This is the rotational constant of the next vibrational state, and so on. And this is the vibrational frequency. Now, you also don't know which vibrational quantum number it is, and so there's another feature of the pattern that you have to dig out. Now, there are ways you can make vibrational assignments, and I'll just I'll say something briefly about that. One is you see a progression like this, and you want to follow that progression to the lowest possible vibrational level, V equals 0. So that'll be following the progression to the blue. And if the progression goes, as a series of lines to the blue, and then ends abruptly as opposed to is dying out, you're pretty sure you found V equals 0. But if it's dying out, you don't really know that you got to 0. And but there are other patterns. If you look at a long vibrational progression, which is presented to you on a silver platter as a nothing but combination difference. You see all of these things that are associated with different vibrational levels, and you can say, well, this is a progression in the same electronic state. Well, then you can see that the progression has nodes. And so the number of nodes is very likely to be the vibrational quantum number for the upper state. And there are other ways you can use this information, but there's a huge, once the spectrum has been simplified to, a simple thing associated with each vibrational state, you pretty much, you can do fantastic things. Okay, so we have now this progression. We determined B from the change in the PR separation. And in order to be able to make J assignments, we need a resolution or precision for PR separations, which is roughly 2B. Because you want to be able to, since they change in steps of 4B, you want to be sure that your accuracy is 1 unit of J, or better than a half unit of J. And a typical monochrometer that you would use for this would be something like a 3/4 meter instrument with a 1200 groove per millimeter grating, and that has a dispersion of about 10 angstroms per millimeter. And so you can make the slits be about 10 microns before you're starting to kill yourself with, when you make the slits too small, you smear out the image because of diffraction. And so 10 microns is okay for visible radiation. So 10 microns is a 100th of a millimeter. And so you can have a resolution on the order of a 1/10 of an angstrom. And what's an angstrom? Well, at 30,000 wavelengths.
How do you make that calculation? How does the size of the grating affect the resolution?
I didn't say anything about the grating. Where does this is a typical number, and I mean it comes from the diffraction equation, but it also comes from my memory that typical monochrometers are either 3/4 meters or 1 meter. They have 1200 groove per millimeter grating, and this is the number that you typically know. I mean, if you work in second order, well, then you get 5 angstroms per millimeter. Or if you have a 2400 groove grating, it's 5 angstroms per millimeter in first order. Now, if it's a lot of grooves, it's a holographic grating, and they don't work very well in second order. So this is a useful number to store. Okay, but the next number, electronic transitions are, let's say, 30,000 wave numbers, 3,000 angstroms. Well, that's interesting. There's a factor 10 there. So if you have a 1/10 of an angstrom, you have 1 reciprocal centimeter resolution. So that's typical what you can get with this sort of an instrument. About 1 reciprocal centimeter resolution. You can measure things to better than the resolution if they're not. Remember, there are these things. There's only 2 lines and they're relatively far apart. And so you can do better than the resolution. You can do better than the resolution by the resolution divided by the signal to noise if they're single symmetric lines. And so you can, with this sort of instrument, have a precision on a PR separation of a few, maybe 2 or 3/10 of a reciprocal centimeter. And as long as B is larger than 6/10 of a reciprocal centimeter, it'll work. But there are a lot of molecules with B smaller than that, and then you have to work a little harder. So this is pretty good for most classes of experiments, but it's right on the edge when B is a 1/10 of a reciprocal centimeter. But one of the things is that you have an interplay between this crude instrument, the monochrometer, and your laser. Your laser, you can have you can measure line centers on the order of 3/1000ths of a wavelength. That's with a CW laser. And again, even with a pulse laser, which has a resolution of 3/100ths of a wave number, you can get to 3/1000th of a wave number precision in spacings. And so the dispersed fluorescence might not be quite precise enough to make rotational assignments. You can then scan through the lines in question, and you can use your laser precision rather than the monochrometer precision. So this is a fantastic thing because just by doing a simple, in this case, a passive double resonance experiment, the spectrum is completely sorted out. And so instead of having to face the usual classical problem of being given everything and trying to find a toe hole to begin to unravel, to take it apart, It's, you know, from the very get-go, you have it sorted. And so this means you can deal with much more complicated problems right away. Okay. Now there are hybrid methods. I said passive double resonance. Well, I'm leading up to double resonance where you have two lasers. But you can also use the monochromator in a way that, I think Sam asked this question. Suppose you use the monochromator not to look at dispersed fluorescence, but to only look at fluorescence that happens to occur within a relatively narrow spectral window. And so here is a four-track parabola. And so what is this? So in an ordinary spectrum, the spectrum isn't spread out as a four-track parabola. It's a bunch of lines in a one-dimensional array. And so in this, the way the figure in the lecture notes is labeled, this is wrong as far as Hertzberg is concerned because red is on the left. And so here's the P branch region, here's the R branch region. This is red. And what's going on here? Well, a P branch always starts out going to the red. And if there is a head in the P branch, then the P branch will turn around and so here's the head and we'll continue out to the blue. The R branch always starts out to the blue. And so in this region, there will be R lines and P lines commingled. In this region, you start out at low J in the P branch, and there's a higher J. Now, there are lines, the low J region of the P branch is in the midst of a lot of traffic. And so, all right, so there are two kinds of experiments you can do. You can set your monochromator to accept a spectral window which is narrow. Maybe there are 3 or 4 lines in that window, and you can set the monochromator either to here or to here. Okay. And so suppose you set your monochromator to accept a window that's relatively near the bandhead. And then you scan your laser. Okay, well, one thing that you would not want to do is scan the laser in the region where the monochromator is set because there will be a lot of scattered light that goes. And so what you will do is scan the laser, and when you go through this region, which is related, which has R branch lines related to the P branch lines you're excited over here, you're going to see some fluorescence in this window. And so there'll be a few lines that appear, and they'll be associated with this. Now, this also intersects this region here, which might be a P branch. So the P branch starts out going like that and comes around. So this might be very high J lines of the P branch, or it might be relatively low J lines of the R branch. And so there'll be another region that corresponds to the lines here, and so there'll be another group of lines. And so you'll be selecting a few J's in the P branch, seeing them in the R branch. You'll be selecting something over here, and you'll see them somewhere else. So if you set the monochromator at this point, there'll be 2 little pieces of spectrum you see. And you know a fair amount about them because you have laser precision in measuring the lines, and you know that they're far away from where you set the monochromator. And then, of course, you do the other experiment. You now set the monochromator where these lines were. And then, when you scan in this region, you see those lines. which you know are related to these, and you have laser precision on them. So you do 2 experiments, and you get little pieces of the R and P branch that you know are related, and you get them with laser precision. And so it's a very, very effective and simple way of doing laser-induced fluorescence, where by using a monochromator you sort the spectrum. Tim Steinle uses this a lot. And I don't know who invented it. I think we did, but it's a pretty simple technique, and it sorts the spectrum.
One thing that you've always warned me about using monochromators is that you lose an awful lot of intensity.
Sure.
Through it. And so, how much of a problem is it for different uses of the monochromator?
Well, you know, for this one, you don't care that much about resolution. The monochromator slit can be pretty wide. And so, well, what does a monochromator cost you? I mean, in a usual experiment, you're studying fluorescence here, and you have some kind of a lens and a photomultiplier here. Okay, so what fraction of the fluorescence can you intercept? Well, it's not unreasonable to say that you can have a 2-inch diameter lens about 2 inches away from the monochromator. And so you can figure out what fraction, what solid angle that is. So, and then if you're using a monochromator or just a bare photomultiplier, the quantum yield of the photomultiplier is the same. So what you really want to do is compare the F number of your optics for collecting simple fluorescence and the F number of the monochromator. The F number of a monochromator is usually, for this sort of thing, is usually 10. F10. Sometimes you get one that's got a bigger grading, and maybe it gets down to 7.5 or something like that. The solid angle is the square of is related to the square of the F1. So you would, with a photomultiplier close to your fluorescence region, see roughly 100 times more fluorescence. Now sometimes, because you don't want to get scattered light, you put a filter here to block the laser. That costs you a factor of 10. You don't need a filter with the monochromator because it's a super filter. And so that takes you down to, now then there's the issue of how efficient is the grading? What, you know, is the grading 100% efficient? Well, holographic gradings are very, very high efficiency. But then there's the issue if you're, is it a blaze grading and which order you work? So roughly, you know, you use a monochromator, you're losing a factor of 10, 100. But yeah. But you can calculate. I mean, there's also how big is the slit and so on. How big is the slit and how big is the photomultiplier and so on. Okay. So you can also do active double resonance experiments. I mean, using the monochromator, it satisfies my rule that you want something that's always going to work. Because what is a monochromator? It's a grating in a box. And again, if the grating drive isn't working well, you knew that before you started the experiment. And if the photomultiplier isn't working well, it's the same thing you do with LIF. So it's a pretty certain thing to work, whereas especially in the 1960s and 70s, the laser was pretty surely not going to work. And if it was working, you want to get data and do something. And so having 2 lasers that are working was hard. And so having a passive double resonance scheme is a great way to do business. But you can also do something like this. So you excite here, and that state selects. That's basically the same thing as the dispersed fluorescence experiment. And then you scan a second laser. So this laser is fixed. And now you scan this laser. And you look either at dips in the fluorescence from this, or as the appearance of fluorescence to the blue of what you would have gotten from here. And you see nothing but combination differences again. And that's a fantastic thing. And this is also better than dispersed fluorescence because you have laser resolution. And this one has Doppler selected. And so there's no Doppler width either. And so it's much better than dispersed fluorescence. But the problem is it requires 2 tunable lasers working. And in the days of CW lasers, that was always a problem. In the days of YAG pump dye lasers, it's not so much of a problem because they're both being pumped by the same YAG laser, and the dye lasers are pretty passive, and so you can do double resonance, and there are even people who with CW lasers now do quadruple resonance. So it's not impossible. It's just asking for trouble. So you can do these 2 laser experiments. There are many kinds of 2 laser experiments, and maybe we'll talk about that someday. Okay, so now you have a technique that enables you to simplify the spectrum. So the assignment, instead of being an elaborate exercise in pattern recognition, is you have this on a silver platter. And so one of the things that you do is say, okay, I'm capable of dealing with a far more complicated spectrum than I would have been by classical methods. And so that's the masochistic approach. If complexity is hard, well, I strip away the complexity by doing double resonance. Now I go for new complexity, which is much worse. That's what I do. Okay, but let's talk about what kinds of new complexity you're going to encounter. I mean, everything I've been talking about up till now has sort of pretended that molecules are in electronic states called singlet sigma plus states, that they don't have any fine structure. And so we haven't thought about details about what electronic state it is. We've only asked, well, what J is the transition, and sometimes a little bit about what vibrational level. But what about the symmetry? And if you have a state that's not singlet sigma plus, there's going to be extra levels, and those are going to make the problem more complicated. So we have lambda, which is the orbital angular momentum projection on the internuclear axis. And this is a source of confusion for a lot of people because lambda is a projection of L, the total orbital angular momentum, but this is not round. This is a not round molecule. L is quenched by the not roundness. There is no L, but the not roundness has a symmetry. You have a unique axis, and so, or you can think of this as a Stark effect, where you have a certain symmetry electric field. It mixes all L's but preserves the projection quantum number, which is lambda. So lambda is usually good, and L is usually not even relevant. And we have spin. We have the projection of the spin. So the spin, unlike L, the spin is not destroyed by the lack of spherical symmetry. And that reflects the fact that spin, there are no spatial coordinates for the spin. The spin is just some mythical beast that physicists have invented for us, and it doesn't know about space not being isotropic or the molecule not being round. So we have these quantum numbers, and omega is lambda plus sigma, or let's call it J. Now, you might think this is a trivial thing. And it isn't, it's in some ways it's trivial, but in some ways it's special. Lambda and sigma are electronic quantum numbers. J is from the rotational quantum, the rotational wave function. So we have this j omega m. That's something that's distinct from the electronic wave function. It happens that omega has to be equal to lambda plus sigma, but it really has two different sources. And a lot of people don't understand that. Okay. So we're going to have states that have additional quantum numbers, and sometimes, okay, yes. And so it would be nice to be able to record a spectrum in such a way that we can determine these quantum numbers for both the upper and lower electronic state. And the critical, the most important method for making such assignments is finding the lowest J lines in each of the rotational branches. And so I'm going to talk about that for a while. How much longer do I have? Not very long. Not very long at all. There's, so we make little diagrams that represent the energy levels. Now in the notes, the diagram is a little simpler than this. This is a sigma sigma plus state, and let's say this is a sigma pi state. And so we put onto this labels for J and parity. And now for pi, we have J equals 1, and we have minus parity and plus parity. And for J equals 2, we have plus parity and minus parity. So a sigma pi state is really two states. And the lowest J is 1, and the parity alternates with J, and they alternate in such a way that you have these two parity, and the lower component and the upper component vary this way. So the first thing you do, the reason you draw these diagrams is it enables you to figure out what will be the lowest J lines. I mean, they're very, very powerful things. But as soon as you have parity and J, you can draw what will be the possible transitions. And so you have to go plus to minus, or minus to plus, so you have a transition there. You have a transition there. And you have a transition there. So this is R0, this is P2, and this is Q1. Those are the first lines. And so for a sigma 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 pi, that's what you can see if you had a and you can work out what the pattern of first lines would be for any symmetry. Now, there's other things here. Plus minus, plus minus, minus plus minus. There is another way of labeling the levels. It's called EF symmetry. And what happens is you multiply the parity by minus 1 to the j, and you regularize things. So all of these levels are E, and all of these levels are F. And what you discover is R and P branches are always E to E, and Q branches are always E to F. As opposed to this less convenient, I mean, you can remember this diagram, but this is much more useful for thinking about what the spectrum is going to be. So you make these little diagrams, and they tell you what to look for in order to make definite assignments. And they also tell you that you'd like to be able to organize things according to patterns, pattern-forming quantum numbers. And so if you look at the bottom of page 5 of the notes, there's a transition between a case B triplet sigma state and a case A, triplet pi state. And in a case B state, the pattern forming quantum number is n, and in case A state, the pattern forming quantum number is j. The rotational energy levels arrange themselves according to B and n plus 1 in this state, and B effective omega j plus 1 here. So we have the energy levels that are always expressed as a quantum number times a quantum number plus 1 times a constant. And for case A, you have a rotational constant, which is maybe slightly different for the different omega components. But you have this way of pretending that you have sigma-sigma states. So you're reducing things to the more fundamental unit, and then you find the patterns you need. And so that's a rushed version of how you use lasers to sort things out. And next time, we're going to actually be talking about states with non-zero S and lambda and building effective Hamiltonians for that.